Okay, so I finished writing down all the different work functions for the different metals. So cadmium is 4.07 electron volts, aluminum is 4.08, silver 4.73, platinum 6.35, lead 4.14. So we see we range from, for these common substances, metals mostly, we range from about 2.28 electron volts for sodium up to 6.35 electron volts for platinum. Okay, so how does this affect um, these observations? So how does this work function factor into these observations? In particular, the observation that there's a minimum frequency for the light below which no photoelectric effect is observed. Well, um, if we accept Planck's hypothesis that the electromagnetic radiation comes in energy chunks that are Planck's constant times the frequency of the radiation, nu. Then, when that energy chunk is a chunk of energy is smaller than the work function of the substance, then we wouldn't expect to see a photoelectric effect because each individual photon, each individual chunk of energy doesn't contain enough energy to kick out even one electron. And since since the energy arrives in discrete packs, like discrete chunks, then you wouldn't necessarily expect that they can just add up. Okay, that they basically they sort of each dissipate individually until you can't actually build up energy. You wouldn't expect necessarily to be able to build up energy from these discrete chunks over time. Okay, so this implies that the minimum frequency, the threshold frequency below which we see no photoelectric effect, is related to the work function. Just in this simple way, it's the work function divided by Planck's constant. Okay. Now, you know, you may wonder why it took so long to sort of come up with the idea that electromagnetic radiation was discretized. Okay, that it was quantized. That is, that the energy associated with electromagnetic radiation is delivered in chunks, and this is probably explained by the fact that Planck's constant is very, very small. We haven't talked about this yet, but if you look at the value of Planck's constant as we now know it, okay, it's something very small, 6.626 times 10 to the minus 34 joules per second, or in a unit which is a little bit closer to what we're doing here, 4.136 times 10 to the minus 15 electron volts times seconds. Okay, that means that since we see that the work function in electron volts is we just have a few electron volts for these work functions. Okay, then we would expect that we would need roughly a frequency of about 10 to the 15th or so seconds in order to be able to observe the photoelectric effect, because anything less than that would give you this chunk of energy which is smaller than the work function. Another way to see this is to convert frequency into wavelength by just frequency is equal to the speed of light divided by the wavelength. Okay, and so now hc, the product of these two constants, is equal to 1240 electron volts times nanometers. And so if you plug in the wavelength of 400 nanometers, which is right at the threshold between ultraviolet and the visible region of the spectrum. So this is basically as small a wavelength as you can get and still be able to just barely be able to see with your eye. Then we find that the energy associated with such a wavelength is 3.1 electron volts, which again will only get us enough energy to observe to see the photoelectric effect for sodium. Okay, and so the fact that the Planck's constant is so small means that these chunks of energy are actually really incredibly small.